Okay, this session is about an introduction to the SpecPR system. SpecPR is a program for analyzing spectra one at a time through a command line interface. It has a long history. Not going to make excuses for it. I've been hoping that better things would come along. This system was started in the 1970s and continues to be developed today. Some new systems have come along, but none have the full functionality of the SpecPR system. First of all, let me show you. If we type SP on a Linux machine and tab, it shows all the programs that begin with SP. Some of these are not SpecPR programs, but many of them are, like spell is a spell checker. But we have SpecPR itself. That's the full analysis system. Then there's other, one that I'm going to use a lot today will be SPPrint, which prints out the contents of a SpecPR file. SpecPR files are binary format. There's an advantage to this idea. But there's also a number of other programs, and I'll illustrate this on the PSI computer pan, which is this window over here. There's Spec Find is as users develop more and more spectral products, taking lab data, telescope, spacecraft data, and put them into the SpecPR format. The SpecPR system catalogs a database of what's available, and we can search that database. First of all, let me show you. If we just do Spec Find, it tells you what the options are. And many of the SpecPR programs will do this. Type the program and return, and it'll tell you what you need. If we do Spec Find -K, oops, I do need to type correctly. There are keywords. So, for example, AREF is absolute reflectance. There was an old way where it's ABS space ref, but that took up a lot of space, so we made a change. Okay, if we look at the options for Spec Find, we can do Spec Find and something like kaolinite. Now, we didn't find any, and there's probably a reason for this. One, you have to have spelling right. Sometimes people capitalize the mineral name, so best to do Spec Find -I, ignore case, AREF, kaolinite, and then we find a bunch. So again, context is everything. I usually include the -I. The Spec Find -E tells how many entries we have. So on PSI's pan computer, we have over 400,000 spectra in the database, 11,000 absolute reflectance spectra. This includes data that are in spectral libraries like the USGS spectral libraries. So this is a nice resource to use. If you find something like, here's the kaolinite, and you want to know where that file is, Spec Find -F and the file name without the colon there, and it'll tell you that's where it's located. If you're going to use spectra from another person, you should check with them to be sure that it's okay. So now let's talk about spectra. Well, in fact, this is a good example. SPPrint and the file name, and you usually want to type that to more or some other paging filter. So this shows the contents of this one file. So there's lots of spectra in here, different numbers of channels. So these are different wavelengths. So what we have here is the record number where the spectrum is, the title of the spectrum, the number of channels, the date and time that it was last processed, the pointer to the wavelengths, and pointer to the resolution. That's the full width half max for each channel. So with that, let's start SpecPR. I've set up a directory here, and there's so normally you type SpecPR or dSpecPR as the developmental version that may have some new features. Currently on this laptop that I'm running on, there's no difference. A restart file name, if you have a restart file, which I don't, then there's nothing in this directory. So I'm going to assign a couple of files, and in this case, the spectral library files, so we can look at some spectra. And then if you want to plot spectra, you need a graphics terminal. So this opens an Xterm window to write the graphics to. The minus sign here suppresses messages about new features if your restart file is current. Okay, so we're going to start SpecPR, and we'll have to assign files. So the first thing when you type SpecPR or dSpecPR is it shows new features, and this is an example of where you can get band depths. If we go, you can page through these and read. These are new features that are not in the manual, so they're new features relative to the last update of the manual. This one is important, which we'll go through in the Tetracorder training. We can add in the Tetracorder spectral features and see what the continuum will look like when we do spectral features. You can do wavelength shifts in the plots so that you can see if a spectrometer has a shift, what it would take to line up a known spectral feature or between two spectrometers. Wavelength markers, you can mark specific wavelengths with colored lines. There's all kinds of features that I won't go through here, but there's a lot of different things you can add. So hitting escape, that's just a more command on a file, and I can show you where that is later. So this the start of the SpecPR, and what we're going to do is we don't have any setup in this directory, so we've got to do that. So we need to do a new restart file, and by convention we just call them R1, and that way when we're searching around for files, we know that any file named R1 is at least in one of the SpecPR directories is going to be a restart file. You can also do R2, R3, and you can name it anything you want. This is just a convention. So SpecPR has 6 files that can be assigned at any one time. In practice, any one file can contain about 1 million spectra, more than 1 million spectra, and you need 7 digits of places to give the record number, and there are some places where that's the limit. If you go over that, you won't see the record number. So you can have more, just that if you want your histories to work out so you can find things, then limit your files to 1 million spectra. And in practice, we've never even come close to that. So for example, on PAN, if we did the Spec Find minus E, we have 400,000 spectra, and that's spread across quite a few different files. So one of the advantages of SpecPR is that it creates a history of every operation you do. And this is important for tracing um, when you have a spectrum that maybe you created a year ago or 10 years ago or 20 years ago, and you want to know, gee, there's something weird about the spectrum, what is in it? You can trace how that spectrum was created every step of the way. Now, to do that, we need to have unique file names, and we need to have a way that we can trace that history, and that's done in SpecPR by the SpecPR file name and record number. To limit the size of file names in the histories, the SpecPR file names must be no more than 8 characters. So you'll see that commonly. Now, in order to not have to type the file name all the time, we have an alias in SpecPR for a file name down to 1 character, and that's the V, U, W, Y, D, and S. And S is a special file name. It's for star packs to do extinction measurements in astronomical observations, where you're tracking a star as it rises or sets to see the changing atmospheric transmission. So here, we don't have any files assigned, so we don't have to type anything, so we just press return. If we're working at an observatory and doing extinction calculations, you can enter the position of that observatory, and there's a couple of observatories where we've worked early on. I haven't updated this list in a while, but you can put in the coordinates of your observatory. In this case, we're not going to do any of that kind of work, so not applicable. Now we assign the individual files. Now what we want is, for this demo, is I was going to install the USGS spectral libraries. So the USGS spectral libraries are located at, and I'm over in this rightmost window, SL1 USGS, and we can do the original or a convolved library. To make it a little simpler, I'm going to do a convolved library where all the spectra are the same. And here we see all of these S06, so I should S06, and I'm hitting the tab key here that does file completion. And we can try something like AV is average, so that'll be spectral coverage from about 0.35 to 2.5 microns. So we can assign that one. If I double click on this, it highlights, and then I can go and paste it. So I can assign this to V. So instead of typing this long name, all I have to do is type a V, and that gets translated to that full path to the file. So if the file didn't exist, it would warn you and say, do you want to really create the file? Sometimes, like if I misspelled the name and there was no file, it would tell me, hey, it doesn't exist, and maybe I wanted to find a file that already existed. So we have that file open. We do need to add the names, but we'll do those in a minute. Let's also go to assign the original file names, the native library, and that is in just library 06, and the native library is splib06a. So we can assign this one, and that also exists. That's good. Okay, we're done there. We don't need to assign anything more. Now we need to type in the actual names. And the reason why these are separate is sometimes a file name is very long, and if the first 8 characters are unique, we can just take those characters and make it, that's the name that'll be used in the history. Okay, now SpecPR has three ways you can have a file in terms of reading and writing. If the file protection is a negative number, it's read-only. So, and we have a convention that if a file doesn't exist in your current directory, SpecPR assigns it as read-only. You can override that, but it's not a good practice, so that you only write to a file that's in your own directory. That way, if multiple users are working on the same file, if it's not in that directory, they don't write to it, so you don't overwrite each other's results. So in this case, I'm just going to accept that. Same with the next one. So now we have the up here at the top, we have the name and what it's assigned to, the letter code, W, and then the protection status. So there's 8219 records, and we can't write to this file. So we probably need another file that we can write to. So let's go back to the setup parameters. So type B, and then reassign files and devices, R, and let's assign you to, and I'm just making up a name here, and I'll highlight that. See, it doesn't exist, so we want to create it. Okay, that way we have somewhere to write Spectra if we want. Now, if we want to keep this as an archive, then we need to assign a unique name that'll get cataloged. An SP temp file will not be cataloged into the database. So we go down here, slash, make this a little wider so it, oops, got to be a lot wider so it doesn't wrap. Okay, so here's, we have an SPS series for spectroscopy, PSI, and then a number, and that's a unique name that will be cataloged, and we can see where things get cataloged, and we can find our data later once we have thousands of spectra. If you're at a different institution, you need to create your own series that's a unique name, and if you use the database software, add that name to the database so it gets searched for. Okay. Now, we have our Spectra and files open, so we do need to add a name for the U. That was, I forgot. It was sptempu. So with Linux, again, if you double click on a word, it highlights it, and then you can go and paste it with the middle mouse button. Very quick. You don't have to do Control C or Control V, or if you type, you can do copy and paste. Those are actually different buffers. So you have two different buffers in Linux. You have the quick buffer and then the Control C buffer. Okay, so we're done with that. Now, we didn't start a window, an X window for graphics. So we're going to exit SpecPR, and then we're going to do the alias. That was this. So I can just type that. Now that alias is something I set up for my login. You can set up something similar. There's xterm, xterm2, and xterm3. And xterm2 is double the size of the graphics window of the default graphics window, and xterm3 is triple the size. But for the laptop, xterm2 is about all it'll fit easily. So I set up 3 windows here so I can look at spectra. Um, and for example, uh, okay, so let's, for example, go and look at this spectrum here. So we can see, to look at spectra, um, it's under T, which is also, you'll see display spectra. So type T. Now, spectra are, SpecPR processes a one-dimensional array at a time, and it doesn't necessarily know what that array is. So it doesn't know if it's wavelength, time, phase angle, or some other parameter. It's just an array. It's up to you to associate that array with Y values and X values. And you do that, in this case, we're going to look at record 77 of, we're looking at 06A, which is W. So we say W77, and then that's the Y values. The X values would be W6, because over here it said our wavelengths are 6. And if we look at record 6, that's the wavelengths. So if we press return, we get a plot. The first time you start SpecPR, it doesn't put up the wavelength mode. It's in channel mode. So let's type A. It gives you your prompts down here. H is channel, A is wavelength, N is energy, which is inverse wavelength. Okay, now we see this is in wavelength. Also, the points are little crosses. I find it's better to use lines. So there's line type 3 is just a line. Then let's try auto scaling. Capital A auto scales. Oh, it doesn't auto scale when we're in this mode. Change scale. Let's change the wavelengths from 0.3 to 2.5, so we have a fixed wavelength, and 0 to 0.3 on the vertical axis. And that's kind of a boring spectrum, but it'll serve its purpose. So if we then do something different, now there's also if you do question mark, you see your history. So we typed W77 capital W6. Let's try W6 capital W77. And if you're ahead of me, it would reflect the spectrum onto this other axis. Oops, why didn't it do that? W6, W77. And we need to change the axis range here. So let's do 0 to 2.55 and a vertical range 0 to 2.55, so they're equal. Now we see it reflected. Okay, and let's go and choose a different spectrum that's a little more interesting, like alunites are a little better. Okay, so let's try this one. That's gotta be sure what we're going for here. That's a different wavelength region. So W1 versus W2 is a different wavelength region. So it'd actually be good to show the different ones. Let's see. Let's try this one. Okay, so W1063, W6. Okay, now if we do W6, capital W 1063, and reflects it on. So you have your choice. You can manage this, or you can use these wavelength pointers. If you don't want to look up the wavelength pointer all the time, in the spectral libraries, they should all be set correctly. So if we go out, W1063 ampersand will put the pointer of the wavelength set in place. Okay, now let's change the scale and zoom in on a spectral feature. Capital S will allow you to do upper left corner, lower right corner. We can zoom in a little more, capital S. Now, and let's auto scale and try and get a little bigger. L1 will show us points. So you have L1, L2 is just a line, L3 is a line, and it'll show the error bars for data that have error bars, and you'll notice this spectrum here has error bars in the next spectrum. We didn't call those up, but if the error bars were large enough, in fact, let's go and do that. If we go out, W1063, and our wavelengths are already set. We don't have to always set them. So if you're working with one wavelength set all the time, you set it once and leave it. Type of E, error bars will be included. Line type 3. The error bars are so small that they're basically smaller than the width of the line. Okay, so let's do a continuum removal of this feature here. So you have all your options are listed over here. A is interactive band analysis. We don't need to change anything, so we'll just type a lowercase a, and then we can type our wavelength position. So I clicked here, and then I clicked over here, press return, return again, return again, return again, and return again, and it gives center, width, depth, and asymmetry. Asymmetry is this distance to the band center divided by this distance from the full width half max to the band center. So this is the equal boundary of the half width point of the full width half max, and this is the computed band center based on the structure of the points down at the bottom of the band. Tetracorder will be using something like this when you use the linear continuum to do the continuum removal. Okay. You can write these results out to a file, but we're going to just get out and do something else. So X gets you out. There are two ways to get out of a program. There's an X and an E. There's a difference when there's a pending operation. An E will get out of the current routine and proceed with anything else that needs to be done. And in this case, there wasn't anything else to be done. X will terminate all future operations that are waiting to be done and go back to one of the main programs, either here or the main X out of here. This is the main section where you jump to other parts of the program. If we go to math, now this is a temporary file, doesn't exist, and the first time you enter the routine, it'll create the file. You won't see that message again. So let's try something. Well, let's take this same W1063 and multiply it by a constant of 2. So it tells us what we're doing. We need to write it somewhere. The only place we can write it would be um, actually we need to go back up. We assigned U. So we can only write to U, and the protection on U says we can only write to record 1. We can tell a title star 2.0. Now it'll be off scale. If we auto scale, we can see now the values are up around 1.6. Let's zoom out. So now our spectrum is way above 1. There's a pending operation. We're in the plot routine, and we can do things. We can delete a point if it's bad. We can change the header information. If we go to the header information, it tells us the title. Here's the history. So it tells us the spectrum and what we did to it. We multiplied by the constant. There's a manual history that is used where you can enter things for complex operations. The regular history isn't enough, and it uses the manual history. Air mass is used in astronomy calculations, and it tells who did the operation. There's a bunch of bit flags. You can go and read those when you have time, and you can change those bit flags. There's dates and times of when the spectrum was processed and when it was first created. So this was created in 1991, and we just did an operation in 2021. Then there's other things about the spectrometer, the scan time and integration time and that kind of stuff. And number of channels, pointer to wavelengths, pointer to resolution, if people entered it, the viewing geometry and temperature. So there's a pending operation. So we can change things. We did this operation, multiplied the spectrum by 2, but we haven't written it to the file. It won't write to the file until we type E to get out. If we type an X, it'll exit the routine, and that pending operation of the write will not happen. So that's called a hard exit. We'll go ahead and exit with the E, and we see now that U has 2 records. And the reason why it has 2 records, let's exit here, list U. There's only one spectrum, but the way SpecPR files are is that they're a fixed record length. And you'll notice in some of these that, for example, in this alunite spectrum here, it starts at record 1019, but the next spectrum doesn't start till record 1031. The other records are hidden records because it takes, there's 4,200 channels in this spectrum, and it takes more than one record to store the data. So in this case, 480 channels takes 2 records. So that's why the protection is at 2. So with that, that's a first introduction. You can list spectra. You have other tools to list spectra. You can plot spectra, and then we'll get into Tetracorder. We'll actually use the new feature where we can enter a Tetracorder set of features and see how they are being applied to an individual spectrum. And so that's a first order introduction. Let's do one other thing, and the default is the information is not turned on. If we type I, we see all the operations you can do. So you can do math operations, multiply, divide, subtract, and you have a bunch of algebraic functions. Then there are special functions, and F1 is a list of special functions, and this describes each one. And you can call them by F1, or you can do it by the short name or the full name. And there are quite a few special functions, and it's not hard to add special functions either. When we get up to F42. This function is the same um, um, algorithm that does the least squares fitting of a spectral feature to an unknown. And in fact, that subroutine that is used in this is what is called by Tetracorder. So many of these subroutines that are in the SpecPR system are called by other programs like Tetracorder. Okay, if you're done with that, you can type E and get out. So that's a first order overview. If you have SpecPR installed and you want to do Tetracorder work, if you don't have another tool that can plot spectra where you can zoom in on spectra and look at spectral features, then SpecPR is an alternative to use. Let me do one other example. Okay, we're going to do two spectra, and GDS82 has two things here. So this one is an IR spectrum. So we have overlays. OV1 equals, and this is W 1019, capital W 42. And we can choose to autoscale or not autoscale, and we're not going to autoscale here. So this overlay is now in place, and it'll be displayed anytime a plot comes up, whether you're in math or this display routine. Then let's bring up this one, W82, and we're still with W6, so we don't have to type W6. So there's the two spectra. If we change the range here, change scale, we're going to do W, let's do 1 to 5 microns, and 0 to, looks like about 0.9. So there's the results from two different spectrometers. This is a laboratory spectrum from a Beckman, an old Beckman that we used back in the 90s. And then the red spectrum is that overlay spectrum, and it's from an FTIR. So we can zoom in and there we see, notice the difference in resolution. So the FTIR is resolving the shoulder a little better. It's almost not seen in the Beckman data. And there's a match of the intensity, but you can see because the geometry is a little different, the way the FTIR works and the Beckman works, you can't expect to be a perfect overlay at all wavelengths. So it's reasonably close, and you saw at to zoom back out, you got to do it by hand. Let's do 1.5 W for wavelength, 1.5 to 4, 0 to 0.9. And we see we have reasonable matches out here. And, you know, all the features are pretty similar, just a small change in intensity. And the resolution changes the look a little bit different. Okay, that's a good introduction to SpecPR. So E gets you back to here, and quit, and we're done.